Everything you learned about space in school is wrong. Well, not entirely wrong, but it is missing the best parts. The universe holds secrets so strange they sound like science fiction. We are about to journey through 30 of them. You will discover facts that will permanently change how you see the cosmos. How can a planet rain glass? Why is the moon slowly abandoning Earth? By the end of this, you will know the answers. What is the one space mystery you wish was real? Our own moon is in the process of leaving us. Every single year, it drifts almost 4 centimeters farther out into the void. This slow retreat is a direct result of the gravitational tug of war between Earth and the moon, a dance of forces we experience as ocean tides. The moon's gravity pulls on our planet, causing the oceans to bulge. But Earth spins so quickly that this watery bulge actually gets dragged a little bit ahead of the moon. That forward pulling mass of water then exerts its own slight gravitational pull on the moon, giving it a tiny energy boost that pushes it into a progressively wider orbit. Think of it like a parent spinning a child in a circle. As the child swings out, they slow the parent's spin. That is exactly what is happening to our planet. Earth's rotation is gradually slowing down, making our days longer, while that lost energy is transferred to the moon, pushing it away. In the distant future, this will have a stunning consequence. Total solar eclipses, where the moon perfectly blocks the sun, will become impossible. The moon will simply appear too small in our sky to cover the sun completely. We will only ever see annular eclipses, those dramatic rings of fire. This quiet, constant drift is a reminder that even the most stable-looking features of our sky are part of an endless, dynamic cosmic story. While our own moon slowly drifts away, far out in the depths of our galaxy, an entirely different kind of cosmic phenomenon is brewing. Drifting through the constellation, Sagittarius is a colossal cloud of gas and dust, known as Sagittarius B2. This is not just any cloud. It is a giant distillery floating in the void. Inside its vast expanse, spanning trillions upon trillions of kilometers, are billions of liters of vinyl alcohol. Imagine a cloud so immense it could fill our solar system many times over, and it is saturated with this complex organic compound. This is not the kind of alcohol you would find in a drink, of course. Vinyl alcohol is a key building block in the formation of even more complex molecules. Its presence out there in the cold, dark space is a profound clue for scientists. How do the raw ingredients for life itself begin to assemble in the emptiness between the stars? This giant cloud acts as a massive cosmic laboratory. On the surfaces of tiny dust grains within the cloud, simple atoms and molecules collide and stick. Over eons, shielded within this frigid nursery, these basic ingredients slowly piece themselves together into more elaborate structures like vinyl alcohol. Finding such a large reservoir of this molecule tells us that the universe is inherently predisposed to chemistry, to building up the very pieces that could one day lead to living organisms. We are essentially looking at one of the universe's first steps toward creating the conditions for life. Every single one of us, and every living thing on Earth, is made from stardust. But before that stardust could become us, it had to go through phases like this, learning to build complex molecules in the dark clouds of deep space. It makes you wonder, if the universe is so good at brewing the ingredients for life, how many other cosmic distilleries are out there, quietly preparing the recipe for existence? That same cosmic chemistry which builds life's ingredients can also forge worlds of unimaginable fury. Venus presents us with a planet of profound and violent contradictions. While its surface takes 243 Earth days to complete a single sluggish rotation, its thick, toxic atmosphere is caught in a frenzy. The entire sky of Venus is screaming around the planet at supersonic speeds, completing a full circle in just 4 Earth days. This is a super-rotating atmosphere, a phenomenon where the air moves 60 times faster than the ground below it. Imagine standing on a world where the ground beneath your feet moves with the pace of a lazy river, but the clouds overhead are a blur, a perpetual hurricane of acid and gas racing around the entire globe. The mechanism that drives this perpetual atmospheric sprint is one of the great puzzles of our solar system. Scientists believe it works like a giant planetary heat engine. Venus is shrouded in incredibly thick clouds of sulfuric acid that trap solar energy with terrifying efficiency, creating a runaway greenhouse effect. This immense heat at the cloud tops creates a tremendous difference in temperature and pressure from the planet's poles to its equator. That differential is the engine's fuel. The atmosphere, trying to balance itself out, rushes from the hot equatorial regions toward the cooler poles. But the planet's slow rotation twists this flow into an unstoppable, planet-wide jet stream. It is as if the entire sky is sliding sideways, forever trying to catch up to itself. This constant supersonic wind whips around Venus, scouring the landscape and contributing to the planet's hellish conditions, where surface temperatures are hot enough to melt lead, and the pressure is equivalent to being a kilometer deep in Earth's ocean. This is a world where the very sky has betrayed the ground, creating a permanent global storm that makes our most powerful hurricanes seem like a gentle breeze. The same cosmic forces that create screaming atmospheres can forge objects of even more extreme and silent violence. Deep within the aftermath of a supernova, a star's core can collapse into one of the universe's most bizarre creations, a neutron star. These are the cosmic zombies of dead stars, impossibly dense and fiercely magnetic. To grasp its density, picture a single sugar cube made of neutron star material. On Earth, that tiny cube would weigh as much as a mountain, over 1 billion tons. The force of its gravity would be so immense it would instantly punch a hole through the planet, falling straight through the rock and magma as if Earth were made of air. This staggering density comes from a catastrophic collapse. When a massive star explodes in a supernova, its outer layers are blasted into space, but the core is crushed. Under this unimaginable pressure, electrons are forced into protons, merging to form neutrons. An entire star, often more massive than our own sun, is squeezed into a perfect sphere no wider than a city. All that remains is a seething ball of neutrons, packed together with almost no empty space. This birth is so violent that the newborn star spins at a dizzying rate, sometimes completing hundreds of rotations every single second. Many of them develop powerful magnetic fields, becoming pulsars that flash like cosmic lighthouses with a rhythm more precise than any atomic clock. For physicists, these dead stars are perfect natural laboratories. They represent a state of matter that cannot be created anywhere on Earth, allowing us to test the laws of physics under the most extreme conditions imaginable. They are the ultimate endpoint of gravity's relentless pull, a place where the very atoms of our reality are squeezed out of existence. What other secrets about the fundamental nature of the universe are locked inside these silent, spinning orbs? While a neutron star represents matter crushed into its most extreme form, the universe also forges worlds of almost impossible luxury. Scientists have discovered planets that are likely made of diamond. One of the most famous is a world called 55 Cancri E, a super-Earth located about 40 light-years away. This planet is believed to be composed largely of carbon, the same element found in pencil lead and in the glittering stones of an engagement ring. Under the immense pressures and searing temperatures within this world, that carbon is likely compressed into a crystalline structure, creating a vast interior of diamond and graphite. Imagine a landscape not of rock and iron, but of glittering, solid carbon. The entire planet could be one gigantic gem, orbiting its star so closely that a single year passes in just 18 hours. The surface temperature is hot enough to melt most metals, creating a world of unbearable heat and impossible riches. How does such a jeweled world come to be? It all depends on the star it orbits. Stars with a high ratio of carbon to oxygen provide the perfect raw materials. In the protoplanetary disk of dust and gas surrounding such a star, carbon atoms would be abundant enough to clump together and form carbon-rich planets, instead of the silicate-rich worlds like our own Earth. The core of such a planet would be a deep layer of diamond, potentially thousands of kilometers thick, possibly topped by a crust of graphite. Some theories even suggest that with the right conditions, it could literally rain diamonds from its skies. While we cannot see its surface directly, artist renditions depict a dark, rocky world glowing with volcanic rivers of lava, a stark contrast to the glittering fortune that lies beneath. It is a place of cosmic irony, a treasure of unimaginable value existing in an environment so hostile that it is completely unreachable. This discovery forces us to expand our idea of what a planet can be. Our own Earth, rich in oxygen and silicon, is built from the most common cosmic rubble. But elsewhere, under a different star, the very building blocks of planets can create something far more exotic and dazzling. If you could stand on its surface, you would be standing on a fortune larger than any ever known, a whole world forged from a single, perfect crystal. Even the most enduring cosmic monuments are not permanent. For centuries, Jupiter's Great Red Spot has been a colossal landmark in our solar system, a swirling tempest so vast that our entire planet could easily fit inside its furious winds. This is not a simple storm, but a high-pressure anticyclone, a maelstrom of gas raging between two jet streams that has persisted for at least 400 years. Yet this giant is slowly fading. Observations over the past century reveal a startling trend. The Great Red Spot is shrinking. In the late 1800s, it was wide enough to swallow 3 Earths side by side. Today, it is barely wider than our single planet. The storm is not only getting narrower, it is also becoming more circular, as if the forces that sustain it are slowly losing their grip. Why would a storm that has endured for so long begin to weaken? Scientists have several compelling theories. One suggests that smaller storms and eddies, swirling in the chaotic Jovian atmosphere, are constantly interacting with the giant. These smaller vortices might be stealing energy from the Great Red Spot, disrupting its flow and causing it to gradually dissipate. Another idea points to internal changes within Jupiter itself. The storm is powered by the heat rising from the planet's deep, hot interior. If that heat flow were to fluctuate, or if the storm were to encounter a different stability layer in the atmosphere, it could alter its structure and speed its decline. The fate of this iconic storm is a window into the complex and dynamic weather systems of gas giants. Its slow disappearance forces us to confront a profound truth about the cosmos. Change is the only constant. We are witnessing, in a single human lifetime, the gradual death of a feature that has defined Jupiter since the invention of the telescope. What will Jupiter's face look like a century from now? Will the spot vanish entirely, or will it transform into something new? A smaller but equally fierce remnant of a dying legend. The fading storm on Jupiter reminds us that the cosmos is a place of constant change, but it is far from silent. We often hear that in the vacuum of space, no one can hear you scream. This is technically true because sound, as we know it, requires a medium like air or water to travel. In the empty void, the vibrations that create sound have nothing to push against. Yet, to call space silent is a profound misunderstanding. The universe is filled with a symphony of invisible energy, and we have learned to listen. Scientists use instruments called plasma wave antennas to capture the electromagnetic vibrations and plasma waves that ripple through space. These are not sound waves you could hear with your own ears, but by translating their frequencies into the range of human hearing, we can experience the cosmos in an entirely new way. The result is an eerie and haunting chorus. The planet Jupiter, for instance, sings a song of crackles and pops, the sound of its immense magnetic field interacting with charged particles from its volcanic moon, Io. The sun emits a low, deep roar, the sound of its turbulent surface and colossal loops of plasma churning. Even the void between galaxies is not empty. It hums with the faint remnant of the Big Bang itself, a ghostly whisper from the birth of everything. Listening to these sounds is like being given a new sense. You are not hearing air molecules vibrate. You are hearing the raw energy of the universe, the very heartbeat of planets and stars, made audible. It transforms the cold, black emptiness of our mental picture into a dynamic and resonant arena. If you were floating near Saturn, you would hear nothing with your own ears, yet you would be immersed in a storm of energy, a silent disco of particles and waves. This hidden symphony forces us to reconsider our place in the cosmos. We are not just observers looking out at a quiet, still painting. We are living inside a performance that has been playing for billions of years, a performance we are only just beginning to hear. Even in the most scorching of environments, the cosmos finds a way to hide its most precious resource. On the sun-blasted world of Mercury, a planet where daytime temperatures soar high enough to melt lead, pockets of ancient water ice lie preserved in the eternal darkness of polar craters. These are not sun-drenched glaciers but secret caches, buried in deep trenches where the sun has not shone for billions of years. Because Mercury's axis has virtually no tilt, the sun always hugs the horizon at its poles, leaving the deep floors of certain craters in permanent, profound shadow. Inside these cold traps, temperatures can plummet to minus 170 degrees Celsius, creating a deep freeze so intense that any water that finds its way there becomes trapped for eons. This discovery shatters our simple assumptions about the solar system. How does water survive on a world that is practically kissing the sun? The ice did not form there from oceans or rain. It was delivered. Comets and water-rich asteroids, the solar system's ancient delivery trucks, have been crashing into planets since the beginning. When one of these icy bodies impacted Mercury, the tremendous heat of the collision would have vaporized most of the water. But some of that vapor would have bounced across the planet, eventually finding its way into the polar shadows, where it froze solid and remained, a frozen fossil of a primordial bombardment. This tells us that the ingredients for water, and perhaps even for life, are not unique to the outer solar system. They were scattered everywhere, even in the hottest neighborhoods. Finding ice on Mercury forces us to rethink the history of our entire planetary system. The same process that brought water to Earth likely also sprinkled it onto the most unlikely of worlds. If water can persist in the unlikeliest of places, then where else in this vast universe might we find it hiding, waiting in the shadows? Even the deepest, darkest voids of space are not truly cold. The entire universe, in every direction we look, holds a faint, uniform warmth. This is the cosmic microwave background radiation, the lingering afterglow of the universe's violent birth in the Big Bang. It is the oldest light we can possibly see, a fossil from a time when the cosmos was a searing, opaque soup of particles and energy. Think of it like a piece of iron pulled from a forge. At first, it glows white hot, but as it cools, its light fades through orange and red, eventually becoming invisible to the eye, though it still radiates a faint heat you can feel. The universe has been cooling for nearly 14 billion years, and this background radiation is the final, cooled ember of that initial fireball. Its temperature today is a mere 2.7 degrees above absolute zero, the coldest temperature possible. This is not a temperature you could ever feel on your skin, but it is a fundamental property of the cosmos itself, a thermal echo that fills every cubic centimeter of space. The discovery of this background glow was one of the most profound accidents in scientific history. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, annoying hiss in their giant horn antenna. They scrubbed away pigeon droppings and checked every connection, but the faint, uniform static remained, coming from every part of the sky. They had inadvertently stumbled upon the cooled remnant of creation itself, a discovery that earned them the Nobel Prize and provided the strongest evidence yet for the Big Bang Theory. This radiation does more than just confirm our cosmic origins. Its subtle, microscopic variations are a baby picture of the universe, a map of tiny fluctuations in density that, over billions of years, gravity would sculpt into the vast cosmic web of galaxies and voids we see today. That faint warmth is the foundational blueprint for everything, from the largest galaxy cluster to the planet you are standing on. It is the universe's birth certificate, and it is all around us, a permanent reminder of our spectacularly hot beginning. That faint cosmic warmth is not the only temperature surprise the universe holds. There are stars out there that are literally cooler than you are right now. These are not stars in the traditional sense, but a strange class of celestial objects known as brown dwarfs. They form just like a star from a collapsing cloud of gas and dust, but they simply do not have enough mass to trigger the sustained nuclear fusion that powers true stars. They are the universe's failed stars, too big to be called planets, but too small to truly ignite. After their brief hot birth, they spend the rest of their immensely long lives slowly cooling down, fading from a dull red glow to near invisibility. The coolest brown dwarfs ever discovered have surface temperatures hovering around room temperature, a mere 27 degrees Celsius, or even lower. Imagine stepping outside on a pleasant day, and the air feels warmer than a distant sun. These objects emit almost no visible light, glowing instead with a faint, deep red or infrared heat that our eyes cannot see. Finding them is one of astronomy's greatest challenges, like searching for a black cat in a pitch-black room. To spot them, scientists use telescopes designed to see heat signatures, hunting for these dim, warm pinpricks against the cold backdrop of space. They represent a missing link in the cosmic family, blurring the line between a star and a planet. A brown dwarf is a celestial ghost, a fading ember that never quite caught fire, destined to cool further into darkness over trillions of years. It is a humbling thought that while some stars are unimaginably hot infernos, others are so cool you could, in theory, warm your hands by their faint, dying glow. The universe's failed stars give way to worlds of pure, distilled fury. Far beyond our solar system, a planet called HD 189733b orbits its star in a vicious, 2-day-long year. This is a gas giant, larger than our own Jupiter, but it is tidally locked. One side of the planet is permanently scorched by its star, while the other is plunged in eternal night. This brutal temperature difference fuels winds of unimaginable violence, screaming across the planet at over 5,400 miles per hour. That is more than 7 times the speed of sound, a relentless supersonic gale that would instantly tear any solid structure to dust. But the winds are only the beginning. The planet's atmosphere is rich in silicate particles, the same material that makes up sand and glass on Earth. In the searing heat of the dayside, these silicates vaporize, rising into the atmosphere. The planet's furious winds then carry these vaporized particles to the frigid night side, where they instantly condense into tiny droplets of molten glass. And then the rain begins. It does not fall down, but sideways, driven by those 5,000-mile-per-hour winds. A horizontal blizzard of scorching liquid glass perpetually scours the entire planet. How can we possibly know such terrifying details about a world dozens of light years away? Astronomers use a technique called transmission spectroscopy. When the planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases and particles in that atmosphere absorb specific colors of this starlight. By analyzing the missing colors in the spectrum, scientists can decode the chemical fingerprint of the air itself, identifying the signature of silicate particles that make up this deadly glass rain. This world is a laboratory of extremes, a place where the very laws of physics and chemistry create a hellscape beyond human comprehension. It forces us to expand our definition of weather from gentle rain and soft breezes to include a storm of molten rock. If you could stand on its surface, your last sight would be a sky full of glittering, razor-sharp shards, moving faster than a bullet, in a storm that never, ever ends. Our sun is about to turn itself inside out. Roughly every 11 years, the star at the center of our solar system undergoes a complete magnetic reversal. Its north and south poles swap places in an event that sends ripples throughout the entire heliosphere, the vast bubble of the sun's influence. This is not a random occurrence, but the peak of a predictable cycle, a period of maximum activity known as the solar maximum. During this time, the sun's surface becomes a chaos of sunspots, which are cooler, darker regions where magnetic fields are exceptionally strong and twisted. These tangled fields can snap and reconnect, unleashing colossal explosions of energy. Solar flares, intense bursts of radiation, can erupt without warning. Even more powerful are coronal mass ejections, billion-ton clouds of magnetized plasma hurled into space at millions of miles per hour. When this solar fury is directed at Earth, our planet's magnetic shield, the magnetosphere, absorbs the blow. The result can be a magnificent celestial light show, the aurora, as charged particles spiral down our magnetic field lines and strike the atmosphere. But the consequences are not always so benign. A direct hit from a powerful coronal mass ejection can induce massive electrical currents in the ground. These geomagnetic storms can overload power grids, potentially causing widespread and long-lasting blackouts. They can also fry satellite electronics, disrupt global positioning systems, and knock out radio communications. The last time Earth experienced a truly catastrophic solar storm was in 1859, an event known as the Carrington Event, which set telegraph offices on fire. A storm of that magnitude today, in our deeply electrified and connected world, would cause trillions of dollars in damage and take years to recover from. This regular 11-year flip is a powerful reminder that our technological civilization is entirely at the mercy of a star whose moods are anything but calm. As we approach the next magnetic reversal, scientists are watching our sun more closely than ever, knowing that our modern way of life depends on predicting its next tantrum. Even as our sun rages with magnetic fury, our own planet holds a secret of staggering scale. We live on a world so rich with life that its abundance defies the cosmic norm. The number of trees on Earth is estimated to be a staggering 3 trillion, a figure so large it eclipses the entire stellar population of our home galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars, a number that already feels impossibly vast. Yet our single planet, a pale blue dot in the cosmic ocean, hosts at least 7 times more trees than there are suns in our entire galaxy. This fact turns our perspective inside out. We often look up at the night sky and feel small, dwarfed by the sheer number of distant stars. But this comparison reveals a different kind of immensity, one of profound, tangible richness right here at home. Each of those 3 trillion trees is a complex living system, drawing water from the soil and energy from the sun, supporting countless other species in an intricate web of life. They are not just silent statues, they are the planet's lungs, the architects of its soil, the anchors of its ecosystems. When you walk through a forest, you are not just walking among trees, you are navigating a tiny fragment of a network that, in its sheer numerical abundance, outnumbers every star you can see on the clearest of nights. This is not to diminish the grandeur of the cosmos, but to elevate the miracle under our feet. Our galaxy is a magnificent swirl of ancient suns and cosmic dust, largely empty and silent. Our world, by contrast, is a teeming arc of biological complexity. It forces a humbling question: if life can achieve such density and variety on this one world, what other forms of abundance might exist on the countless other planets that must orbit those 100 billion distant stars? The universe is vast in its emptiness, but here on Earth, it is vast in its fullness. Saturn's magnificent rings are a cosmic lie. Those iconic, glittering bands of ice and rock, which seem as eternal as the planet they circle, are actually a fleeting feature in our solar system's history. Recent data from the Cassini mission revealed a startling truth. The rings are far younger than anyone suspected. They likely formed a mere 100 to 200 million years ago, a blink in cosmic time when dinosaurs still roamed the Earth. Saturn itself is over 4 billion years old, meaning for 95% of its existence, it was a plain, ringless world. How did such a colossal and beautiful structure appear so late in the game? The leading theory points to a violent and chaotic birth. A moon that wandered too close to the giant planet would have been torn apart by immense tidal forces. Alternatively, a massive comet could have been shattered in a catastrophic collision. The resulting debris, millions of chunks of pristine water ice, was then shepherded by Saturn's gravity into the impossibly thin, flat disk we see today. Their youth solves a long-standing mystery about their brightness. Space is filled with dark dust, and over billions of years, this dust should have gradually coated the rings, turning them a murky gray. Their brilliant, reflective whiteness is a testament to their relative newness. They simply have not had enough time to become dirty. This also means their future is limited. The rings are not a permanent monument. They are actively raining down onto Saturn. Micrometeorite impacts and pressure from sunlight are slowly but surely dragging the icy particles out of orbit, pulling them down into the planet's atmosphere in a constant, invisible shower. Scientists estimate they could be completely gone in another 100 million years. We are living in a uniquely privileged moment, a narrow window in cosmic time where a giant planet wears a crown of ice, a beautiful and temporary wonder destined to vanish. The cosmic abundance of our own world is mirrored by a profound emptiness elsewhere. Drifting through the constellation of Boötes is a region of space so vast and so barren it defies comprehension. This is the Boötes Void, a spherical chasm in the cosmos measuring an almost unbelievable 330 million light-years across. To grasp its scale, picture our entire Milky Way galaxy, 100,000 light-years wide, and then imagine a void so huge it could swallow thousands of galaxies with ease. Yet within this staggering volume, astronomers have found only a handful of isolated island universes. If the universe were a city, this void would be a central park the size of a continent, containing just a few scattered houses. Its existence poses a monumental challenge to our best models of cosmic structure. The prevailing theory of the Big Bang suggests that matter should be distributed relatively evenly, clumping into the great cosmic web of filaments and clusters we observe. A void this size should not exist. It is far too large and too empty to have formed through gravity alone. So what could have carved out such a nothingness? One compelling, though unsettling, theory involves not dark matter, but dark energy. This mysterious force, which drives the universe's accelerating expansion, may have acted like a cosmic pressure, actively pushing matter away from this region in the distant past and preventing galaxies from ever forming. Alternatively, the void might be the result of multiple smaller voids merging over billions of years, like soap bubbles combining into one giant cavity. Or it could be evidence of something even more exotic, a colossal collision with another universe in the multiverse, a scar left on the fabric of our own reality. The Boötes Void is more than just an empty space. It is a question mark written on the sky. Its profound silence forces us to confront how little we truly understand about the forces that shaped everything. It stands as a chilling reminder that the universe is not just a collection of brilliant lights, but also an immeasurable expanse of shadow, and that the deepest mysteries are often found in the places where there is nothing at all. While the Boötes Void presents an almost sterile emptiness, life in our own cosmic neighborhood has proven to be far more tenacious than we ever dreamed. Certain organisms on Earth do not merely survive in space, they thrive in its brutal conditions. The most famous of these cosmic hitchhikers are tardigrades, microscopic eight-legged animals often called water bears. These creatures are virtually indestructible. They can withstand the complete vacuum of space, blistering solar radiation, and temperatures ranging from just above absolute zero to well above the boiling point of water. How is this possible? Tardigrades possess a superpower known as cryptobiosis. When faced with extreme dehydration, they curl into a tiny, barrel-shaped ton, shutting down their metabolism to an undetectable level. In this state of suspended animation, they are not truly living, they are waiting. Their cells are protected by special proteins that form a glass-like shield, preserving their essential structures until they are rehydrated, sometimes decades later. But the resilience does not stop with these tiny animals. Bacteria like Deinococcus radiodurans can endure radiation doses thousands of times stronger than what would kill a human. It repairs its own shattered DNA with astonishing speed and accuracy, earning it the nickname Conan the Bacterium. These extremophiles are not just laboratory curiosities. Their existence has profound implications for one of the oldest questions: are we alone? The theory of panspermia suggests that life's building blocks, or even life itself, could travel between worlds, hitching rides on asteroids, comets, or cosmic dust. If a hardy microbe can slumber inside a rock, shielded from the worst of space, it could potentially survive a journey from Mars to Earth, or even from one star system to another over millions of years. This means the seeds of life may not be unique to our planet, but could be scattered throughout the galaxy, dormant and waiting for a warm, wet world to awaken them. We may all be descendants of interstellar travelers, and the life we search for in the stars might be closer than we think, sleeping in the dust beneath our feet. Our galaxy is on an inevitable collision course with a cosmic neighbor. The Andromeda Galaxy, that faint, smudged spiral we can see in a dark sky, is not a distant monument but an oncoming train, hurling toward us at 250,000 miles per hour. In approximately 4.5 billion years, the Milky Way and Andromeda will meet, beginning a gravitational dance that will utterly reshape our celestial home. From Earth, this event would not be a cataclysm of exploding stars, but a slow, majestic, and beautiful transformation. Over millions of years, the familiar band of the Milky Way would begin to warp and distort in our night sky. Andromeda would grow from a faint smudge into a brilliant, sprawling disk, eventually filling half the heavens. As the two galaxies began their first pass, their immense gravitational fields would pull and stretch each other, flinging out long, luminous streamers of stars, gas, and dust in a slow-motion tidal ballet. The skies would fill with new, unfamiliar constellations as stars from Andromeda joined our own. The core of this merger is not a violent crash, but a graceful intertwining, because galaxies are mostly empty space. The trillions of stars within them are so far apart that direct collisions are incredibly rare. The solar system will likely be flung into a new, wider orbit, but our sun and its planets will probably remain intact. The real violence is reserved for the gas and dust clouds. As these vast nebulae collide, they will compress, triggering a ferocious burst of new star formation, a stellar baby boom that will light up the merging galaxy with brilliant blue-white newborn stars. After this first pass, the two galaxies will swing apart, only to be pulled back together by gravity, eventually merging into a single, larger galaxy over another 2 billion years. Most astronomers call this future entity Milcomda, a giant elliptical blob of stars. The familiar spiral arms of our Milky Way will be gone forever, erased by the gravitational turmoil, and replaced by a more featureless, glowing haze. This cosmic union is a reminder that even the largest structures in the universe are in constant motion, part of an endless cycle of creation and destruction that operates on timescales we can barely comprehend. Our galaxy as we know it is temporary, a beautiful, swirling snapshot in a much longer and grander story. Saturn's North Pole conceals a geometric wonder so precise it seems artificially crafted. A colossal hexagon, wider than 2 Earths placed side by side, wraps around the planet's pole in a 20,000-mile wide pattern of swirling clouds. This isn't a solid structure but a persistent 6-sided jet stream, a raging river of air with each side longer than our entire planet. For decades, its stark geometric perfection has defied simple explanation, appearing more like a cosmic symbol than a natural weather phenomenon. How can a fluid atmosphere, governed by chaotic forces, produce such a rigid, angular shape? The secret likely lies in the physics of spinning fluids. Imagine a pot of water on a spinning turntable. As the speed changes, the water's surface can form stable waves with 3, 4, or even 6 sides. Scientists believe a similar process is at work deep within Saturn's atmosphere. A fast-moving jet stream at a particular latitude may be acting as a barrier, and the differing rotation speeds between this stream and the planet's interior could be generating a standing wave, a stationary pattern that doesn't move with the wind. This creates a self-reinforcing loop where the atmospheric flow is pinned into a hexagonal shape. The Cassini spacecraft provided stunning visuals of this phenomenon, revealing that the hexagon is a towering structure, a wall of clouds that extends deep into the atmosphere, with each side acting as a sheer cliff where wind shears reach staggering speeds. Inside its boundaries, the weather is strangely contained, a colossal whirlpool capped by this impossible geometric frame. It is a natural laboratory for fluid dynamics on a scale we cannot replicate, a reminder that the universe often writes its most beautiful equations not in numbers, but in clouds and storms. What other geometric secrets are hidden within the turbulent atmospheres of distant worlds, waiting for a patient observer to decode their silent, spinning logic? That same geometric perfection on Saturn is governed by a deeper cosmic rule, one that reshapes the very fabric of reality. Massive objects do not just sit in space, they bend it. A galaxy or a dense cluster of galaxies warps the space-time around it so profoundly that it becomes a lens. Light from more distant objects, traveling through this warped region, does not follow a straight line. Its path is curved, just as a marble would roll along a curved indentation on a stretched sheet. This phenomenon is called gravitational lensing, and it turns the universe into a house of mirrors and magnifying glasses. We see multiple, distorted images of the same background galaxy stretched into faint arcs and rings of light, a cosmic mirage known as an Einstein ring. This bizarre effect is not just a curiosity, it is a direct and stunning confirmation of Einstein's theory of general relativity. His radical idea that gravity is the curvature of space-time itself was proven correct by observing starlight bending around the sun during a solar eclipse in 1919. Today, gravitational lensing has become one of astronomy's most powerful tools. It allows us to see galaxies that are otherwise too far and too faint to detect, their light amplified by this natural telescope. But the true magic of lensing lies in what it reveals about the invisible. The amount of bending we observe often implies far more mass than we can see in stars and gas. The lens is being created by the gravitational pull of dark matter, the mysterious, invisible substance that makes up most of the universe's mass. By mapping how light is distorted, we can literally chart the distribution of this hidden cosmic scaffolding. We are using light itself to trace the shape of the unseen, to feel out the invisible architecture of the cosmos. Every warped image and Einstein ring is a message, a confirmation that our universe is not flat and static, but a dynamic, flexible fabric where mass writes the rules and light simply follows the curves. What other invisible realms might we map by watching the light bend? This staggering emptiness in the cosmos finds a strange parallel in a game played on a checkered board. The number of possible ways a single game of chess can unfold is greater than the number of atoms in the entire observable universe. It is a fact that bends the mind into a pretzel. The universe contains roughly 10 to the power of 80 atoms, a 1 followed by 80 zeros, a number so large it defies any human sense of scale. Yet the number of potential chess games is estimated to be around 10 to the power of 120. That is a 1 with 120 zeros after it, a number exponentially more vast. To put that into perspective, if every atom in the universe were itself a miniature universe, the total number of atoms in all those nested realities would still be fewer than the number of possible chess games. This is not a measure of size, but of pure abstract complexity. A chessboard is a finite grid with a handful of pieces following simple rules, but the branching pathways of decision and consequence are practically infinite. After just each player's first move, there are 400 possible board positions. After the second move, that number explodes to over 70,000. The tree of possibilities grows so wide and so deep so quickly that no computer, even one the size of a planet, could ever map every single variation. This is the power of exponential growth, a force that can generate more potential outcomes from 64 squares than from all the stars and galaxies we can see. It reveals that infinity is not just a property of cosmic space, but of possibility itself. The universe is bound by physical laws and a finite amount of matter, but the realm of thought and logic can create landscapes of complexity that are, for all practical purposes, without end. It forces a humbling question. If a simple human game can contain such an immeasurable depth, what other infinite worlds of possibility are waiting to be discovered, not in the distant stars, but in the patterns of our own minds? Our own sun, a solitary monarch in the sky, is not the only possible star for a world. Some planets are born into a double sunrise, orbiting not one, but two stars at once. These are circumbinary planets, and the most famous among them is Kepler 16b, a world that science fiction fans instantly recognize. It is a real-life Tatooine. This gas giant, about the size of Saturn, orbits a pair of stars locked in a tight 80-day dance around each other. One star is a smaller, cooler orange dwarf, while its partner is a tiny red dwarf. From the surface of this distant world, you would see two distinct shadows, and your sky would be lit by a pair of setting suns. The rhythm of day and night would be a complex ballet of overlapping light, and eclipses as the stars periodically passed in front of one another. How can a planet find a stable orbit in such a chaotic gravitational environment? The secret lies in distance. A circumbinary planet must orbit far enough away from the stellar duo that their combined gravity acts as a single central point. It is like a planet orbiting a star, but that star is actually a binary system. The planet Kepler 16b traces a wide, circular path around both of its suns, a testament to the delicate gravitational balance that can exist in these multiple star systems. For a long time, astronomers doubted planets could even form in such turbulent neighborhoods, fearing the competing gravitational pulls would prevent dust and gas from coalescing. The discovery of Kepler 16b proved that planet formation is far more robust and versatile than we thought. It suggests that these twin sun worlds may be common throughout the galaxy. If you stood on a moon orbiting this planet, you would witness a sunset unlike any other, a sky painted with the light of two different stars, one perhaps tinged orange, the other a deep red, casting an alien double twilight across the landscape. Our own moon is not the silent, still world it appears to be from Earth. It has its own version of earthquakes, a phenomenon called moonquakes. The Apollo astronauts left behind seismometers on the lunar surface, and the data they sent back for years revealed a world that groans and shudders. These tremors come in several distinct types. Some are triggered by the same gravitational tug of war that causes our ocean tides. as Earth's pull stresses and flexes the moon's rigid interior. Others are the sharp, sudden jolts from meteorite impacts, the moon's surface being struck by space rocks since it has no atmosphere to burn them up. Perhaps the most fascinating are the thermal moonquakes. The lunar surface endures the most extreme temperature swings imaginable. For 2 weeks, it bakes in relentless sunlight at over 100 degrees Celsius. Then it plunges into a deep freeze of minus 107 degrees Celsius for another 2 weeks of night. This dramatic heating and cooling causes the brittle crust to expand and contract, making it crack and pop with seismic energy. These quakes are not like the brief, violent shakes we experience on Earth. Our planet is geologically active and damp, with water helping to absorb and muffle seismic waves. The moon, however, is dry and rigid, a single giant bell. A moonquake can resonate for an hour or more, the vibrations echoing through the cold rock in a long, drawn-out hum. This tells us that the moon is far from geologically dead. The Apollo seismometers even detected shallow tremors along thrust faults, suggesting the moon is still slowly contracting as its hot interior cools. Listening to its seismic whispers gave us our first detailed map of the lunar interior, revealing a layered structure with a solid inner core, a fluid outer core, and a mantle, much like Earth's, but on a smaller, quieter scale. This hidden activity transforms our celestial neighbor from a distant, inert rock into a dynamic world with its own inner life, a place that still talks to us if we know how to listen. That rhythmic shudder of moonquakes is a gentle tremor compared to the orbital sprint of other worlds. Some planets race around their stars so fast that a birthday happens every few hours. One of the speed demons is a planet called TOI 1685b, a rocky world not much larger than Earth that completes a full orbit in less than 18 hours. A year there, from one sunrise to the next, is shorter than a single Earth day. This planet exists in a state of perpetual, blistering proximity to its star, locked in a gravitational embrace so tight it defies earlier theories of how planets form. How can a world survive so close to its sun? The conditions are apocalyptic. The surface temperature soars to a searing 1,200 degrees Celsius, hot enough to melt rock into global oceans of lava. The planet is almost certainly tidally locked, meaning one hemisphere is a permanent, incandescent day of boiling stone, while the other is a perpetual, scorching night. The atmosphere, if it ever had one, has likely been stripped away by the intense stellar radiation, leaving a barren, broiling rock. The very existence of these ultra-short period planets was a shock to astronomers. Standard models suggested that a gas giant could migrate inward, but a small, rocky world like this should have been consumed by its star long ago. Its survival forces a rethinking of the final stages of planetary evolution. Perhaps it is the dense, burnt-out core of a former gas giant, its outer layers vaporized by the star, leaving a planetary cinder behind. Or maybe it formed further out and was gently nuddled inward by gravitational interactions with other planets, settling into this dizzying, close in orbit without falling into the fiery abyss. This world is a test of endurance at the very edge of destruction, a reminder that the cosmos is filled with survivors in the most unlikely of places, orbiting so fast that their years fly by in the time it takes us to have a single night's sleep. We have mapped the stars and galaxies, yet we are blind to almost everything that actually exists. The glittering cosmos we see through our telescopes, all the stars, planets, and nebulae, is nothing more than a shimmering froth on the surface of a deep, dark ocean. This luminous, ordinary matter the stuff that makes up you, me, and every star we can see, accounts for a paltry 5% of the universe. The rest, the overwhelming 95%, is made of two profound and invisible mysteries, dark matter and dark energy. Think of the universe as a grand cosmic pie. If you were to slice it, a tiny sliver, just 5%, would be all the atoms and light we know and love. A much larger piece, about 27%, would be dark matter, and the final, dominating 68%, would be the most baffling ingredient of all, dark energy. So what exactly are these shadowy components? We cannot see dark matter because it does not interact with light at all. It does not emit, absorb, or reflect it. We only know it is there because of its immense gravitational pull. When astronomers measure how fast galaxies spin, they find a shocking discrepancy. The visible stars and gas at a galaxy's outer edges are whirling around so fast that the galaxy should have torn itself apart long ago. The only explanation is that each galaxy is embedded within a gigantic, invisible sphere of matter, a dark matter halo, whose gravity is the only thing holding the spinning galaxy together. This unseen scaffolding dictates the large-scale structure of the universe, guiding how galaxies form and cluster together. Dark energy is even stranger. It is not matter at all, but a property of space itself, a repulsive force that is causing the expansion of the universe to accelerate. Imagine blowing up a balloon with tiny dots on it, representing galaxies. For decades, we thought the expansion from the Big Bang was slowing down as the dots moved apart. But observations in the late 1990s revealed the dots are moving apart faster and faster, as if someone had suddenly started pumping the balloon with more vigor. That mysterious, unexpected push is dark energy. It acts against gravity, driving galaxies away from each other at an ever-increasing rate. The greatest puzzle is that we have no idea what they truly are. Dark matter could be a yet undiscovered particle, a billion of them passing through your body every second without a trace. Dark energy could be the intrinsic energy of the vacuum of space, a concept that leads to calculations which are spectacularly, embarrassingly wrong. Together, these two invisible forces control the ultimate fate of everything. One pulls the cosmos together, the other rips it apart. We live in a universe dominated by phantoms, where everything we can see and touch is nothing but a minor afterthought in a vast, dark reality. Even on a frozen world at the edge of the solar system, the ground can heave and erupt. Pluto, that distant dwarf planet, is home to volcanoes that spew ice. These are not the fiery mountains of Earth, but cryovolcanoes, and they are among the most telling features on its frigid surface. One of the largest right mons stands several kilometers high and stretches over 150 kilometers wide. Instead of belching molten rock and ash, these frozen giants likely erupt with a slow-moving slush of water ice, mixed with substances like ammonia or methane. This icy magma, called cryomagma, oozes out and freezes instantly in the minus 230 degrees Celsius temperatures, slowly building up the distinctive domed shapes we observe. The very existence of these cryovolcanoes is a revolutionary clue. They suggest that Pluto is not a dead, frozen billiard ball, but a geologically active world. For such massive structures to form, the dwarf planet's interior must retain enough heat to keep a portion of its water ice mantle in a malleable, semi-liquid state. This points toward a staggering possibility, a vast, slushy ocean of water lurking beneath Pluto's icy crust. The heat required to power this activity likely comes from the slow decay of radioactive elements in its rocky core, much like the heat inside Earth. This hidden warmth, trapped for billions of years, might be enough to maintain a subsurface sea in perpetual darkness. The discovery forces us to completely reconsider what it means for a world to be alive. Geological activity is not solely the domain of planets basking in solar warmth. It can persist in the deepest freeze, driven by an inner fire we never expected. If a small, distant world like Pluto can harbor such complexity, what other frozen realms at the edge of our solar system might also hide secret liquid oceans beneath their icy shells? That brilliant light warming your skin did not have an easy journey. The photons that leave the sun's surface and race toward Earth in a mere 8 minutes began their lives in a far more arduous struggle. Deep within the solar core, where nuclear fusion forges new atoms, a photon is born in a flash of energy, but it does not simply zip outward toward freedom. It immediately slams into a densely packed atom and is absorbed. A moment later, that atom spits out a new, identical photon in a random direction. This is the start of a marathon game of cosmic pinball, a process scientists call a random walk. Each photon is absorbed and re-emitted trillions upon trillions of times, zigzagging its way through the sun's searing, opaque interior. It bounces from the core through the radiative zone in a drunken, inefficient path. If a photon could travel in a straight line from the core to the surface, the trip would take just over 2 seconds. But because of this constant, chaotic scattering, the journey can take up to 200,000 years. The sunlight you see today was generated in the core when early humans were first beginning to walk the Earth. It spent eons trapped in an internal traffic jam, slowly inching its way outward as part of a vast, glowing energy current. Only when it finally reaches the sun's outer layer, the convective zone, does its journey change. Here, massive bubbles of hot plasma carry it the rest of the way to the surface in a relatively swift ascent, like a cork rising in boiling water. Once it bursts through the photosphere, the sun's visible surface, the obstacle course is over. The photon is finally free, launching into the void and crossing the vast gulf to Earth in a clean, straight shot. This incredible timescale reveals the sun not as a simple ball of fire, but as a dynamic, layered entity. Its brilliant surface is just the exit door for an energy that has been patiently fighting its way out for hundreds of millennia. Every sunbeam is a message from a deep and ancient past, a testament to the slow, powerful heartbeat of a star. That same magnetic architecture which shapes our solar environment also builds a colossal gateway right over our heads. Wrapping around our entire solar system is a vast, invisible tunnel of magnetic fields, a structure so immense it defies easy description. Astronomers call it the local bubble, or more poetically, the local interstellar cloud, but recent observations suggest it acts like a giant magnetic corridor. This tunnel is not made of solid walls, but of ropes and sheets of magnetized plasma, sculpted by the combined winds of nearby stars and the remnants of ancient supernovae. Our sun and its planets are currently traveling through this tube, this local fluff, as if we were passengers on a train moving through a mountain pass. One of the most stunning implications of this tunnel involves a mysterious cosmic static that has puzzled astronomers for decades. When radio astronomers first pointed their instruments at the sky, they detected a persistent, faint hiss that seemed to come from all directions. This is known as the galactic radio background. For years, its origin was a mystery, but the structure of this magnetic tunnel provides a compelling explanation. The tunnel's magnetic walls act like the cavity of a giant flute, trapping fast-moving electrons. As these electrons spiral along the magnetic field lines, They emit a faint but pervasive radio whisper. We are essentially hearing the hum of the tunnel itself, the resonant frequency of our local cosmic neighborhood. This structure also plays a critical role in shielding us, or at least filtering, the galactic cosmic rays that constantly bombard our solar system. These high-energy particles, accelerated by distant black holes and exploding stars, are partially deflected and redirected by the tunnel's magnetic walls. It acts as a first line of defense, a cosmic buffer that moderates the intensity of the particle rain that reaches our inner solar system. This means the space weather we experience is not just a product of our own sun's activity, but is also shaped by this larger architectural feature we are passing through. Our local celestial environment is far from a random void. It is a structured and dynamic realm, and we are living deep inside one of its most fundamental structures. What other invisible geometries are we drifting through, completely unaware of their presence and their gentle influence on our world? These cosmic gateways are forged by stellar engines spinning at impossible speeds. A pulsar is a rapidly rotating neutron star, the collapsed core of a giant star that went supernova. When that star explodes, its core collapses under immense gravity, squeezing a mass greater than our sun into a sphere no wider than a city. This conservation of angular momentum causes the star to spin up dramatically, just as an ice skater pulls their arms in to spin faster. The result is a celestial dynamo rotating hundreds of times every single second. As it spins, its intense magnetic field funnels radiation into narrow beams that shoot out from its magnetic poles. If these poles are misaligned with its rotation axis, the beams sweep through space like a cosmic lighthouse. From our vantage point, we see this as a regular, repeating pulse of radiation with a rhythm more precise than any atomic clock on Earth. Their incredible regularity makes them invaluable tools for testing the universe's fundamental laws. Astronomers use networks of these pulsars as a galaxy-sized gravitational wave detector. As ripples in spacetime from distant cosmic events pass through, they minutely alter the precise timing of the pulses we receive, allowing us to sense the universe stretching and squeezing around us. They have also provided some of the strongest evidence for Einstein's theory of general relativity, with the famous double pulsar system showing how their orbits decay exactly as predicted due to the emission of gravitational waves. These stellar gyroscopes are nature's most perfect clocks, born from stellar death and now keeping time for the cosmos itself, their silent, rapid ticking a testament to the violent forces that shape our universe. Gravity's intricate dance reaches a stunning crescendo in a system known as HD 188753. Here, a single gas giant planet orbits the primary star, while two other suns whirl around each other in a tight embrace, all three locked in a gravitational waltz. This is not a simple binary sunrise, but a celestial system with a triple hierarchy. The planet must cling to its parent star in a wide, stable orbit, far enough away that the gravitational pull from the two companion stars does not tear it loose and send it careening into the void. From the surface of this hypothetical world, the sky would be a spectacle of perpetual motion. The primary sun would dominate the heavens, but the two other stars would appear as brilliant, inseparable points of light, circling one another in a frantic dance. They would never set, instead tracing complex, intertwined paths across the sky, casting multiple, shifting shadows that create a light show of endless, overlapping sunrises and sunsets. The concept of day and night would be beautifully chaotic, with periods of single, double, or even triple daylight, followed by a brief, profound darkness when all three stars are temporarily below the horizon. The existence of such a planet challenges our most fundamental ideas about where worlds can form. The turbulent gravitational forces in a triple star system were thought to prevent the calm accumulation of dust and gas needed to build a planet. Yet here one is, a testament to nature's resilience and versatility. It proves that planet formation can occur in even the most crowded and chaotic stellar neighborhoods, forcing us to widen our search for habitable worlds. If a planet can find stability amid three competing suns, what other impossible skies are waiting to be discovered? Our reality might be a magnificent illusion, a cosmic sleight of hand. The universe you see in three vast dimensions, with its galaxies, stars, and planets, could be a holographic projection from a two-dimensional surface at the very edge of everything we know. This is the holographic principle, a theory that sounds like science fiction, but emerges from the deepest puzzles of theoretical physics. The idea first took root in the study of black holes. When an object falls into a black hole, it seems to vanish forever, lost behind the event horizon. This creates a paradox, because the laws of quantum mechanics state that information can never be truly destroyed. So where does the information about that object go? Physicists like Stephen Hawking and Leonard Susskind wrestled with this, and a startling solution emerged. The information is not lost inside the black hole, but is instead encoded on its event horizon, the two-dimensional boundary from which nothing can escape. The entire three-dimensional content of the black hole is perfectly described by the quantum bits, or pixels, painted onto its two-dimensional surface. The holographic principle boldly suggests that this might be true for the entire cosmos. Our three-dimensional reality, with all its richness and depth, could be a projection from a flat, two-dimensional shell that surrounds us at the unimaginable distance of the cosmic horizon. We are living inside the hologram. This is not a claim that the world is an ethereal illusion, but that its fundamental operating system, the code that describes everything from the spin of an electron to the birth of a galaxy, requires only two spatial dimensions to be written. The third dimension, the feeling of depth and volume, emerges from the complex interactions of that underlying code, much like a three-dimensional movie emerges from the data on a flat, two-dimensional screen. This principle offers a tantalizing path to uniting the two great but conflicting theories of modern physics, quantum mechanics and general relativity. Quantum mechanics describes the bizarre world of the very small, while general relativity describes the force of gravity and the curvature of spacetime on large scales. The two have stubbornly refused to be merged. The holographic principle suggests that gravity itself, the last force to be quantized, may not be a fundamental force at all in the bulk of the universe, but rather a consequence of the quantum entanglement of information on the lower dimensional boundary. We are like characters in an incredibly sophisticated video game, experiencing a fully immersive three-dimensional world, while the entire game is actually running on a flat, two-dimensional chip. The solidity of the ground beneath your feet, the vastness of the night sky, the very sensation of moving through space, all of it would be a magnificent and convincing projection. If this is true, then the ultimate nature of reality is not stuff, but information. The universe is not made of things, but of bits, and we are part of its cosmic code. We have journeyed through a cosmos that defies the classroom textbook. From our drifting moon and screaming Venusian winds to diamond planets and the silent hum of the cosmic microwave background, these 30 facts paint a portrait of a universe that is dynamic, bizarre, and endlessly inventive. This is not the sterile, quiet space you were taught about. It is a living, breathing arena of ice volcanoes, supersonic glass storms, and invisible dark matter scaffolding. Each discovery peels back a layer, revealing not just answers, but deeper, more thrilling questions. The universe is far stranger and more wonderful than we ever imagined. So, which of these cosmic secrets captivated you the most? Let us know your favorite fact in the comments below. If this journey into the unknown left you in awe, subscribe for more explorations into the universe's greatest mysteries. And never stop looking up at the stars with curiosity, for the next great revelation is waiting, just beyond the next twinkle of